So I'm looking at the calendar. You see the calendar?
Yes. Yep.
Okay, so we kind of briefly talk about last week about the final exam. So I intend the lecture will be end by this Thursday, 16, right? Because we have 1 week ahead of everybody else. Because we make up that during the week where they will be studying. So there'll be no lecture 21 or 23rd. My intention is to give the final exam on 23rd. Would that okay with you guys? The official exam date is May 1st for our class. But we had to break out our exam into lecture portion, which is the, and then there is a take-home version. They made a coding version, which I'll give you 24 hours to finish. So would be 23 is good for you guys?
Yeah, so the in-class is going to be like 1 hour and a half?
The in-class will be 1 hour and a half, yes.
Okay.
What topic is going to be covered in the final?
The final exam will cover the book itself. It would not cover this AI part. So it'll be, you know, whatever lecture we went through, and you know, we tested most of them in the midterm. So there'll be some problem in the later half, but it will cover everything. And they again, it's an open book exam, just like a midterm. I will have some few problems which you can work it out during hour and a half. Now the question to hand it in. So you really need to prepare it. You make sure that you know how to take a picture of your work and upload it by the end of that hour and a half to the Sakai side. Is that issue or not?
Yeah, I think so. Just like we have to take a picture of our written work.
Yes.
Yeah, that should be fine.
So you had to take a picture of written work and upload to Sakai side.
Mm-hmm.
So that's the way and it should be submitted within 10 minutes or so after the exam is over. I'll give you something like that, 10 minutes or 10-15 minutes to upload it.
Just to clarify, is this test going to be cumulative, or and is it going to focus more on the second half of the class, or just cover everything? Because I'm not sure.
I haven't made the exam yet. Of course, there'll be, but you know, if you cover, it's accumulate, it's cover everything. But obviously, it's not completely even distributed through all the chapter. There'll be a little bit more on the later chapter because we didn't test that in the midterm. Yeah. But you will, so therefore you'll be including all the work, yes. Any other questions? Okay. So everybody's okay with the time?
Yep, should be fine.
Okay. And basically, I will have a problem up on Sakai, and they'll be released just before the exam. Some of you, I remember some of you had class before this one, right? Any of you has class before 12:30?
No.
Not me, but
Somehow
yeah,
I thought last
somebody
I thought last week when I asked, somebody said they have class before this.
I think Matthew.
We can't hear you, Matthew.
No, we cannot hear
Matthew,
you.
we cannot hear you. Is it Matthew was the one who?
Yes.
Oh. Okay, well, he did not respond. I think he's have some problem. Maybe he should send you a chat.
Yeah, he just did. He just did.
Huh?
He just sent a chat.
Why come out? It doesn't show up on my. Where's my chat message? I didn't see it. I should have chat message. Where is my chat message? Okay, chat. Okay, I got it. Okay, all right. Matthew said she had his. Okay, so we still at start at 12:30. Okay, 12:30 and finish at 1:45. All right. Now, any of you tried it out? The challenge task with this playground. No, no, you.
I messed around with it a little bit, but then nothing much came out of it.
Anybody was successful to come up with configuration which are able to classify this too? Matthew, we cannot hear you.
Well, at least he can share his screen if he did.
Okay. Then just say, can maybe just say, can you share your result?
We still can't hear you, but I could see that you were mouthing. Can you hear me? For what it's worth.
Huh?
He's talking to Matthew.
So he's able to talk to
No, he
somebody?
was not really, but like.
Oh, he cannot share the screen. Okay. So something's wrong. All right. Okay. How to do this? Not much.
Hello.
Oh,
Hey.
Oh yeah, we'll get
can
you
hear me?
now.
Okay,
Yes.
okay.
All right. So tell us what do you try?
So it was a little complicated. I took a screenshot of it, but I think I used all of the inputs except x1 times x2, and then the network, it was something like 8765 neurons in each layer.
8, 7, 8, 7.
8, then 7, then 6, then 5, something like that.
Oh. Okay.
And then so it'd have 6 neurons in the layer that you have 5 in right now, and then 5 in the output layer.
A 5 output layer.
Yeah. And then also I increased the ratio of training to test to 90%.
Training. Oh, you do a lot of more training.
Yes.
Yeah.
Mm-hmm. So I increased that to like 80 or 90% and decreased the batch size to like 5.
Oh.
And then I think that most of the time got it under 0.01. I think I also turned the learning rate like way down too, to like 0.01 or something.
Okay, actually not bad. Are you guys able to see my screen?
Yeah. Yes.
So actually, no, it look. So this is roughly what Matthew said. It's look like actually doing something, right? You see, you get a spiral. This a spiral blue structure, and the spiral. Yeah. So I think that seems to be decent. Okay. Yeah, I think it is here now. I don't know whether they have put a noise that will make a difference or not. So I guess noise will make it. So
it just takes longer with a low training rate. I didn't try it with noise.
Mm-hmm. Okay, so we're not going to spend the time. So basically, say if you play around with this, it is feasible and to come up with a architecture which can do the things that we want to do. So this gives you idea that even though we have machine learning, we have AI, but the human design is still very crucial to some of this, of course, it just play around. Some of them is just simply luck, and then very often, of course, there are specific problems we try to solve that human may still have intuition, which machine, of course, has no clue. Okay, we are now going back to our handwritten digit recognition. So, any you are able to get this on the Colab?
Yes.
Yeah.
All of you?
Yeah.
I hear 2 yes.
Yes.
Okay. So now so I have this things on my Windows. So let's just quickly go through this again. And so the task is to recognize the individual digit, right? Which is a small picture, able to recognize handwriting. And this first part is just input, or just import a necessary library like NumPy, which we use often, matplot library for showing the figure. But for the machine learning part, specifically is this torch and torch vision, which is doing the main thing. This line is simply to recast the data, the image in terms of tensor format and the proper normalize. So it's in proper format, standardized format. Now this is the uploading the data from the database, okay? And there's the one parameter here is the batch size, right? Batch size, remember what is the batch size referred to? Any of you?
The amount of training images.
Amount of training image. Not quite is amount of training image, you know?
Oh, well, actually, is it the amount of images per test?
Yeah, it's number of image you train per epoch. You say. Now remember this. Let me get to the architecture first. Right? They basically say we have this image which digitized by 28 by 28 pixels. So total together is 784 pixel, right? So and each pixel is now it's grayscale. So everything is a grayscale image. So it normalizes. So each pixel now has a value between 0 and 1. Right? Presumably 0 is white and the 1 is black, or vice versa. It doesn't matter, but in between 0 and 1. And then we build in the neural network. In this case, in this example, it got it got 2 hidden layer. That's the intermediate hidden layer, which has 128 neuron. And the second layer has 64 neuron, and then output layer has a 10 neuron. Now instead, normally we just say yes or no, 1 neuron to decide output. Here, of course, we want to 10 digit. And so therefore the output of this neuron is actually represent the probability of whether the image which being input is 0 or 1. So if down here there's an example, just a second. For example here, so basically here's the image, is the input, and then output that is a probability. Say what is the probability for each of the individual digits. So each of this neuron in output corresponding one more digit. All right. So and the probability is normalized between 0 and 1. So in this case it's 3. Then after if the network work properly, it will producing a probability say is a 3. So now the whole, as we talked about last time, the whole architecture, whole point of this neural network or deep learning and reinforced learning, there are many different ways of talking about it. Deep learning is basically had to do with, say, this number of neuron a layer actually has many layers, so it's deep. The network is not just one layer, 2 layer. It's many layer. Convolution neural network is basically means this it's convoluted. That means the whole thing actually, the output actually get feedback back to the network, and the reinforcement learning basically say, okay, I change this way depend on my learning, because my learning presumably we input the image here, and then if this image is 3, the output should be say the digit corresponding to 3 has a probability close to 1. Everything else equals 0. If it's different from that, then we take the difference that we call loss. We'll come to a little bit detail exactly how to measure loss. And that loss, of course, depend on all this weighting factor, all this connection and the bias. And what we want to do is to take a gradient of this loss. You want to minimize this loss relative to all this weighting, or what we call, we can generally say, parameter in the network. So one way is so we can feed into one image, and then we get out of one result here, and that result will depend on all this weight. You can take a gradient of these things and then do steep descents. And the problem with that, if you're doing one by one image, that is very inefficient and slow. So the idea of batch is to say, I do this not just one image. In our case, we do 64 image, and out of 60, so we have 64 output, and you average output of a loss, you average over the loss, so you kind of have average loss, and then the average loss, you calculate a steep descent grade, steep gradient descent, and then reinforce all this change all this weight. So that is the idea of the batch. So one batch, you going through, you basically calculate all this loss, average over the item in the batch, and then you propagate back to reinforce the training, and then epoch referring to how many of this batch we're feeding into it. So one epoch is to say one batch, and then 2 epochs is feeding another batch, and so on and so forth, until you get some kind of convergence, or which is measured by this loss function, right? This loss function. So that is a epoch and a batch. So we'll come back to the beginning. So when we loaded this image, it's loaded up with this batch size. So basically, it's load one time a 64 image, right? 64 image. Now this is something actually you can change yourself. You don't have to do 64 because the database is just a bunch of the image, right? And it basically say you load 64 at a time into this loader. But you can do 32, you can do 16. Actually, I play around with it. You can do a different number. Now usually you do this something like 2 to the certain power, because that will make it a little more efficient in terms of data storage and the memory and the processing. So so let's see, and then here is just to recast. Well, this just to show what is size of image, what size of image, and this line is basically showing an example of image. For example, this is the first image, and let's just print out the first 60 image, what it looked like. So I have this since running here. Now let's me. Do you guys have your since on your computer?
Yep.
Can you run from the beginning, just together with me, and see what do you get, and see what is everybody's get same result or different result? So import the package, import of range, my Google Drive. This is download the data set. Now,
Actually, does this? Hang on a second.
So for example, here is the batch size 64, right? So you actually can use a different size, but let's stick with 64 for a moment. And then exploring the data, print out the first image. And my first image is 4. What do you guys get? If your first time running it, you're loading the data may take a while.
I got 4.
3.
8.
Okay, so it is kind of random. Right, every time you load it, I think it presumably is random. But the first image, now you can try this. For example, instead 0, you can do 1, and then you would say second image. What is like? In my case, my second image is 5. You know? So it's 5. So and then this is just printed out the 60 image as array to just give example of what the image look like. What is 60 a batch? Well, it's not quite batch. I was trying to print out 64, but somehow I get into wrong island. Some kind of some of this function didn't quite doing right. So now and then this is a network. Okay, this is a network. Now you can change this network here. So the network is defined here. So the input, of course, is fixed because it's a 28 by 28 pixel. And the hidden layer is, in this case, 128. The first layer, 128. And the second layer is 64, output layer 10. So first, so it's there's 2 hidden layer, 128 and the 64, and then there's 1 output layer which is 10. So this is something you can this 2 line, for example, is well, you do want the output size to be 60. So this line is something you can vary with. Right? You can change to different number, for example. I want to, for example, let me just try and change to something which is simple. So maybe I'll just say 16 and 8, just for fun. So so my network is 16 and 8, and so then this, the key is the model is defined by this long line. This define a model. So it's first it's a neural network. It's sequential. That means basically say feed from one into another. Right? A sequential container model will be added in order as they pass in the constructor. So basically say, okay, the first layer is that's input size, which came from the input size, and then the hidden layer, there's 2 hidden layer. Remember we defined 2 hidden layer. So therefore is the first one is to connect the input to all the hidden layers. So basically say every of this pixel being fitted into in my case, it's 16 of this neuron, and then each of this neuron again is fed into the second layer, into every one of that. So that's basically what it means. Now, the key thing is here is instead the sigmoid function, they use this Leroux the loop. Now, did I talk about the loop last time already?
Yeah.
Yes, but
I did talk about the loop already. So it's a electrical. It's basically it's a very crude approximation of sigmoid, but it's very very efficient in terms of computation purpose. In fact, actually, so this is now what it. So this is the first. So from input to the first layer, and then from first layer to second layer. So first layer in this case will be 16, and then go to 8, and then again the model is a loop. And then from the second layer, hidden layer, to the output size. And now there is a key statement here, say this neural network is using the loss function to calculate so-called log sort max. And this is something I want to mention, to talk a little bit. So this statement is simply print out a model, right? So now I want to switch to talk about this log sort map, because there's something I think is actually. Now I go to this this online book which we have been using somewhat. So this is actually all the way to I jump to improving the neural network. So jump to this chapter, okay, improving the way neural network learn. Obviously, I will not go through everything here, but the first idea is this cross entropy cost function. Now, usually the cost function, the simplest cost function when we do minimization, for example, when we do linear regression, for example, or minimize function, usually we take the prediction, compare with the true. So we take prediction, compare with true, we take a difference, right? And then we square it, and then we add it all together. And that's how we do a minimization typically. And that is usually, intuitively, that will be loss function. You want it. I mean, you take so for example, if I input a digit of 3, and I get the probability of this 10 probability coming out of each individual output, and this probability I would like to have to be the 3 1 give you 1, everything else 0. So the ideal response is to say 0 0 0 1 and 0 0 0 everything else. And of course, its output here actually is not. So you take difference of those digits between the predicted value and the true value, and you square it and sum over. And that will usually, intuitively, you think of it as a loss function. But it turned out that particular way of doing this is not a efficient. So here is an example of that. So say, here is a simple, this is the example. Let's make pick an initial value as 0.6, and then, so this let's go through this example. This example is simply say that ideally we hope that and expect that output neural network will learn fast from the error. So let's say if error is big, then we do a big change. If error is small, we do a small change. So here he has a simple neural network, simple one neuron, and essentially it's a minimization task. And basically you have weight, and you have bias, and and then you can run this in. So you can run this in. So this is to say how many times it's run, efforts run, and try to do. And so input is 1.0, output is 0.09, and so it kind of pretty good. The cost function going down very fast, right? But now, if you choose a slightly different initial weight and a bias, here is another one. Now you can see, yes, its learning initially started very slow, and only later on is fast. So even though the cost function is very big, namely the loss is very big, but it seems to be learning very slowly. It doesn't go down until it gets to some critical stage, and it's fast going down. So this usual square loss function actually is not very optimal. And so usually using the quadratic cost function, which is the predicted value with two values squared, and then we try to minimize. This is what typically show. Instead of doing that, and going using the sigmoid function, people found that this concept of a cross entropy function is actually much more efficient. And I want to get across this cross entropy function for you. So again, here is let's say a neuron which has 3 input and 3 weight and the bias, and then of course you weight the sum of this input, add the bias, you get A, and then you fit it, and then you get Z value. Z value then fit it into sigmoid function. You get A. This A then is normalized between 0 and 1. Going through a sigmoid function, and that will be your output. The output from neuron is A, and now the cross entropy function is defined as the following. Here, n is the number of total number of items in the training data, and this sum is over all the training set, and xy is corresponding desired output. Okay, so x and the y is you sum over all the x, and they given the x input, and the y is the desired output. Okay, so basically if this function is called cross entropy function. I won't go through the history of where it's coming from, but it turned out that using this way of defining the cost function is much more efficient. So here at here's a simple mathematics going into behind it why that's the case, but let's just look at the simulation. So here's using this cross loss function to run it. So again, if you have good initial point, it's going up, learning very fast. And if you have poor initial guess away function, it's also a weight and the bias is also learning very fast. Okay, so that cross function has this unique clock entropy has this unique property. If you go back to the definition, it's basically so you look at this is suppose your A. Suppose to say your A probability is very good, so A is very close to 1. Then this term go to 0. Okay, this term go to 0. If A is very poor, then this term go to 0. If A is if close to 0, then this term go to 0. Okay, so so this function has some unique property which make this learning somehow speed up much more efficient. So this is one crucial improvement in calculating the loss function. So that's one concept. Is a cross loss function. Now there's a second part which I'm going to run into. This is using cross. That's the second important. Let me go through that. So I want to go skip all this. If you have time, you can read it. But it is all about history. Is this so-called softmax? The idea of softmax, which softmax is define new type of output layer for our neural network, which begin in the same way as a usual neural network with a sigma layer by forming the weighted sum. So you calculate the weighted sum from previous layer, and then you go to sigmoid layer, you get A out of Z. However, we don't apply sigmoid function to get output. Instead, in softmax layer, we apply so-called softmax function. And it turned out this kind of instead using sigmoid function, using softmax definition, this kind of transformation is very good for output where you are trying to predict probability, because this function automatically normalizes between 0 and 1, just like the sigmoid. But the key thing is that this, the sum over all this A together is automatically giving you 1. This is, you know, it's a little bit like a entropy idea in like a partition function, not entropy. The partition function, if you learn statistical mechanics. How many of you actually learn statistical mechanics?
I got the chemistry statistical mechanics, but
You heard of
yes.
a partition function?
Most certainly, yes.
Anybody else? No. So okay. So it's a statistical function. Is the partition function is a very important quantity in statistical physics and statistical mechanics, and this actually is a borrow from that. So this is the proper normalized. If you look at this function, you sum over all A, it's automatically give you 1. So therefore, you know, if you try to predict something which is a probability, you know, you have 10 possible outcomes in our case, because the net probability add together had to be 1, because what it had to be 1 of those guys. So this particular one, so here is the example of different Z, and if you change Z, you see, usually you change Z because you change all this output, but this softmax automatically correlate one with another such that all the probability add together is automatically to be equal to 1. So that's the kind of one advantage of this softmax. So softmax and the cross entropy definition of loss, those things together is now what commonly used for the predicting the probability kind of outcome, a classification. So that is what going on in this, when we define this network model. You know, this line, okay, this line is, we use log softmax as a output of this log softmax. So actually the output is a log of probability. So that is what. So this is something you can play around. You know, you can change different. You can add 3 layers, for example, or change the number of neurons, just like the tensor playground now. But here is more concrete one for this. So if you are interested, you can play with this parameter. You can play with the number layer and see whether you can speed up or get a better prediction than what they have here. Okay, so that is a log softmax. So it's a log of function of this softmax probability. So that is defined as a for the output. And then next it defines so-called negative log Lightfoot loss. It is useful to change, and this is basically the cross entropy loss, what I talk about. So negative log Lightfoot. So this is a cross entropy as it's so to change that as a cost function. So that is what this next few lines is. So it defines the criteria, namely the loss, as negative log Lightfoot loss function. Okay, negative Lightfoot log function. And then this image, so each image has a corresponding label. For example, if the image is 3, the label will be, say, is 3. Okay, so that means that particular image corresponds digit to 3. So this is now loaded from the training data. You know, it's from the training data, and then this is just simply a function to view what the particular image look like. And this one is a log probability. So once you have output, so you input this image, you take one of this image, you put into model. So this is a line which is actually the model propagate the initial image through the model, through this two hidden layer, and then you get output of that. That is a log of probability. So output is a log probability of function. Now, actually, the loss criteria is using the criteria. Criteria is already defined as a negative log, negative likelihood loss. And then so it's compare the output with the label, which is true result, and that give you the loss. Okay, so this is to say, given image, you propagate through, you get a loss. Okay, and then after that you do backward propagation. So you taking that loss, and then you backward propagate into by changing the weight. So this is basically. So here is a example of what weight looked like before you back propagation. And next one is to say, okay, it's now the core of training. So training essentially consists of following. So you define the epoch here is 15. So this is something you can change it too. You don't do, basically say it run 15 times of 64 batch. Right? Each batch is 64 image, then you do it 15 times. So and of course every time you load up new 64 image to do the training. Okay, so it's runs through this E into number of epoch. All right, and you start with the loss equal to 0 initially, and then given the epoch you have 64 image. So for image label in the training loader, remember training loader every time is load 64 image. That's what it does. Okay, and then basically this will convert the 28 by 28 image into basically a vector if you want it. So into a long vector, into a vector of 684, which is now is a input. Input is a vector of length is 784. So it convert two-dimensional data into one-dimensional data by flattening it out. You set the initial optimization equals 0, so everything is set to 0 in the gradient case, and then you calculate output given an image. So calculate the output, and then from the output you calculate loss. This is what is the loss. Okay, and then you take this loss, you propagate backwards. Okay, backwards, and then using the optimization step. You optimize these things using the backwards, and then you calculate loss. Okay, so and then you run through all the image in a batch, and you accumulate all the loss, and then we printed out the loss. So see, this just for our visual purpose to say what's the loss after one batch of training, and then you run after one epoch training. And then you do that again for 15 epochs, and that is, and then finally it's print out the number. So we have that going on here. So we define the image, the log probability, the criteria for the training, and this is just to give example of what the initial weight it is. And then we define optimizer. This optimizer is uses so-called stochastic gradient descent. Now, gradient descent, you all remember what it is, right? It's basically saying we take the gradient of our loss with respect to the parameter we're trying to optimize, and then we just take the maximum gradient with descent. Now, because there are so many parameters, and then we're doing 64 of them as a batch, so there are many of this possible gradient. stochastic gradient basically say you kind of randomly sampling a subset of it, and then from that you determine which direction you go. So because this is the case where often it's used when it's not possible to explore all of possible space. So you do a stochastically randomly pick up a sampling of possible direction you can go, and from that you choose one. So they are, and this is something again you can change. You can change the learning rate. You can change the momentum. I forgot what is the momentum referring to. So this is something you can play around with. Okay. And this just to print out initial weight for the purpose to just for our visualization, and then take an update step, and this just showing, say, if you do one step, what does it look like? Okay, what does it look like? So the way to get changed, for example, if you take the gradient and then you back propagate, the way you get changed. Okay, update the way. So this just show you a little bit inside what example look like. And then we go through this core training stage. So now I'm doing here instead 15, because 15 take a while to run. So I'm taking liberty to take this to be 5, for example. So let's run 5 APOC. And they should, it take a minute to run these things. So while you wait, you can run through your Colab and go through to this step and tell me what you get after 5 APOC. So as you can see, I started with a loss function which is pretty high, 0.9. After 5 run, it's go down to 0.23, which is not great. What do you guys get?
I got 0.15.
You expect 0.105. Okay, that's pretty good. After 5?
Yes.
Okay.
0.13.
0.13. Okay, so kind of random, you can see. All right, and then this is just a function to output the proper image, what look like. So so here is showing what this image look like. So and this will be say if I input this image. So after that learning, now our network. Now notice this is loaded from validation loader. This is not from learning set data. This is from validating data. Right? I take one of the image. First image, for example, is and then it's a 3, and then the prediction to say yes, you see indeed the probability is very good. It is 3. Now if you try another one. Now this one, yeah, if you think about, if a human probably can discern this is a 7, right? This is 7, so it looks like a pretty good 7. Some of this image, this is clearly is 9, very easy to see. This is 7, 4. Now if you look at this one on my screen, the correct answer is 8, but it has also, you see, it gives you final probability to be 5 and 2. So maybe there is a chance to say this look like 5. And it's also say has final probability 2. So this is where, it is a little bit unambiguous that, whether this is truly is 8 or not. You can see that. Right? So this is say it could be 3 or 2. So this is some example. Here is very clear 4. Some of them are very clear. If you look, some of them, of course, is ambiguous. Most of them are pretty clear. Like this. This one actually is interesting. For example, it has an almost equal probability to be 7 and 5. And then it's pretty 5 is just barely a little bit higher than probability 7. Right. So so you do have a case where this, I think human were able to predict this is probably much more close to 5, like 7. Yeah. So anyway, this gives you a feeling of what the output is giving the input. And then next module here is simply running through the testing, all the testing case. I think about 10,000 length. So number of testing images, 10,000 length. And is compared with the true label, with the true label with predict label, whether it's correct or not, and its output of probability. So in this case, I only did 5 epoch. And if I run it, I get probability of 93%. Okay. So if you guys run it, what do you got?
$95.
Yeah, I got 95 as well.
Uh-huh.
I got 97.
You got 97.
Wow.
Oh, you got a 97 with a 5. I wonder whether you did it. Did you run this already before? Or you run it from the very beginning?
I just clicked it recently.
Uh-huh. Well, now you notice that you can, if you after this step, you can go back to here and run another 5, for example. So I define f of 5. So I can run this again. It will pick up where you left over. So I already get 90. I already get the loss is a 0.2 something previously. So if I run another 5, yeah. So you can see the loss now it keep decreasing, and my prediction will go up a little bit. Yes.
Did anyone else get an error when they were trying to show the images with the predicted output?
You get error?
No.
Yeah, it said view classify wasn't defined.
You might need to go to runtime and just rerun the entire notebook.
Yeah.
Specifically, rerun the box right above it, because that's where like its view classify is actually defined.
Yeah, I have not run into view error yet. I did run into error when I tried to change to show 64 image, and I couldn't quite get to show all the 64 image. I did run into error. So now after 5, you see kind of slow in my case. It's going from 0.22 to 0.19. It's not really improving. I'm going to run 5 more times. See, because after 15, I think the loss function should go down to like mine now is converted very slow. So this, I think I just have bad luck. This one, last one, I think is much more faster. Yeah, I only get 0.17. That I don't think that's improved great deal, but let me try to test. So from 93%, it's improved 1%. So it's only 1%. Now you can save all your model, because once you have something which is good, you can save the model. Now, I tried this morning with a different number layer. I didn't try different number layer. I tried different number neuron in each layer. I also changed the batch size. I didn't get that much more improvement, I have to say. it seems to be output is similar. I haven't tried more layer yet. But I think the best I get is basically 97. I think the best I get is 97. I didn't get anything better than 97%. So you guys can try and see whether you get something better than this. But so let's give you an idea. Is based on this template, you probably can build some neural network to do certain simple things. I will imagine, right? You guys should be able to do this if you have simple tasks you want to do. Anybody get the questions?
No.
Nope.
All right. So this is to give you.
Oh, I actually do have one question. Hang on a second. It was kind of like in the previous, like with the sequential command or whatever from PyTorch, like with using like in sort of like connecting the network together. So it's like underneath that
Model here.
Yes. Like, is there any specific benefit from using like multiple modeling methods, like ReLU and sigmoidal or something like that?
I think ReLU is a very efficient one to do this.
Yes,
now,
but like, say you have ReLU like connecting the input layer to hinted layer 1, and then have like a sigmoidal thing connected.
So you say you use a different sigmoid. You use instead ReLU. You can make a tangent, just like this. Tensor.
Yeah, I was wondering if you had any input.
I don't know, and you can try it out, see whether that's something improved. Yeah.
Interesting. Okay.
So I think the reason why your model took so long is because you made the network a lot smaller here with 16 and 8 neurons.
Oh, I forgot I was playing this. Yeah, I don't think this. Okay, so I had 16 and 8. I forgot to mention
because it was like 128 and 64, right? Something like that.
That's right. I forgot to change it back. 128 and 64. That's what they initially has. Yes. So that's why my result was poor compared with you guys. Yes. So but you can say, if it's 16.8, it's not a lot of different from 128. So basically say when, it's very easy for most, if you think about it, if you look at this image, most of the image actually is pretty clear. So you just have very simple model you should able to. So 90% of them is a kind of trivial. Doesn't matter what is throw up, is very easy to recognize. It's nearly the last few percentage is that's very difficult to improve. So up to 93%, 94%, I think for a long time that is people get stuck there, and then the people are able to build a model and get to 98%. I think that for a period of time that was an open challenge in this particular task in the research community. Basically there's a challenge of who can get the best prediction. But now this, of course, is become a toy model for learning. It's no longer it's challenging problem. So this is something you can play around with, and definitely. So it's kind of interesting. This particular example is as simple enough, and I think I find this an explanation of how they build the model and then where there's a function is pretty straightforward. So we are able to cover these things in 2 lectures, and essentially, after 2 weeks, you can tell. You can put in your resume, for example, say you understand neural network, you know how to build a simple model to do handwritten digit recognition. Now, one of you is a computer. Who is a computer science major? I forgot. Is it Matthew?
Yeah.
Okay. Did you take any class in this area?
I haven't, no.
Do they offer any class on this area?
They do. I think the computer sciences department's class on this is very mathematical. So you go into like all the probability and linear algebra behind this.
Yeah. That I think of course they're training for the backup, but they really should have some a class which tied to some practical example, and that I think is what interesting is. But as I said a couple of weeks ago, this is a rapid developing area, and there's a lot of interesting, exciting stuff coming out of that. So I'm pretty much level a technical aspect of this part, and in Thursday we're going to just watch some maybe some video and maybe have some general discussion on the broader aspect of the whole area, you know, in terms of ethical implementation, implication, where we're going, and those are also very interesting aspect of things, you know. But in terms of give you exposure to this area, I think this very much is what I intend to do, and I hope this at least now you can have some idea to say this is, you know, when people talk about neural network and talk of machine learning and the AI, you know what's behind this. Okay. Anybody else has a question?
Nope.
Nope.
Well, if that's it, and we're wrapping up today. That will be all I want to say today. So I'm glad you're all able to get this to work, and so you at least now know how to build a network using PyTorch. All right. With that, we are done today, and see you on Thursday.
All right.
All right. Thank you.
Yeah.
Bye.
Bye.